In this video, we are continuing with the textbook questions. Explain why an organic liquid vaporizes at a temperature below its boiling point in steam distillation. So when a liquid has to vaporize, its vapor pressure should be equal to the atmospheric pressure. So in steam distillation, water as well as the organic substance, both of them will basically are mixed, right? Because you have the steam getting added to the organic liquid. So this in turn makes sure that the total vapor pressure becomes equal to the atmospheric pressure. So the addition of the vapor pressure of both the liquid, that is the organic liquid, as well as water gets equal to the atmospheric pressure. And that is why it is easier to convert them into vapors. And this in turn will make sure that it gets distilled at a temperature lower than its boiling point. So that is why we have the the liquid vaporizing at a lower temperature than its boiling point in steam distillation. Next one, will CCl4 give a white precipitate of AgCl on heating it with silver nitrate? So when CCl4 reacts with AgNO3, it leads to the formation, it will not give any white precipitate, because if you remember, the reason we converted basically the nitrogen, the chlorine, sulfur, all of them, we converted to form the sodium fusion extract. In this sodium fusion extract, the reason we formed it in the first place was to convert it from a covalently bound atom to an ionic bound atom, right? So this CCl4, chlorine atoms are present, but when it undergoes the reaction with AgNO3, it will not undergo any reaction with AgNO3. CCl4, on the other hand, we should have gotten the sodium fusion extract, and then if we use that sodium fusion extract with AgNO3, then we would have gotten the white precipitate of AgCl. The next one, why is it necessary to use acetic acid and not sulfuric acid for acidification of sodium extract for testing sulfur by lead acetate test? So basically, when you have the sodium fusion extract, that is Na2S, reacts with lead acetate to lead to the formation of lead sulfide. Okay, but if we used H2SO4, what would have happened is the lead acetate would have also interacted with the H2SO4 and lead to the formation of PbSO4. Now, this would have hindered the formation. This is a white precipitate and it would have hindered the test. And that is why instead we use acetic acid and not sulfuric acid. Next one, in the organic compound, this one, the pair of hybridized orbitals involved in the formation of C2C3 bond is. Now, we all know that if you have a carbon atom which has a triple bond, it is sp hybridized. Double bond would be sp2 hybridized. Single bond is sp3 hybridized. The issue, the question over here in this question, this problem is the fact that we need to assign priority. It has to do with both the hybridization state of the carbon atom as well as, this question in itself, as well as the functional group's priority. So alkene gets more priority than an alkyne, or rather a double bond more priority than a triple bond. So we start numbering from here. So this becomes the first carbon, this one's the second, this one's the third. So the second and the third, second is sp2 hybridized, whereas the third is sp3 hybridized. Okay, so again, this question is to do with, first we need to figure out which is the second and the third carbon. Because if we went 1, 2, and 3, then it would have the answer sp and sp3 is what we would have picked. But because double bond gets more priority, this is the second carbon and this is the third carbon. So the answer is sp2, sp3. The next one, in Lassigne's test for nitrogen in an organic compound, the Prussian blue color is obtained due to the formation of this particular compound, Fe4, FeCN6 thrice. We discussed about this in the detailed discussion about, detailed explanation of the Lassigne's test. Next one, which of the following carbocation is more stable? So carbocations and stability. So if a carbocation is a primary carbocation, it is going to be less stable than the secondary. So order of stability is tertiary is more stable than secondary, which is more stable than primary. So in this case, we have been given 4 different carbocations and we need to figure out which is the most stable. Generally, the most stable one is a tertiary carbocation. This is exactly is a tertiary carbocation, and this is the most stable. This is due to the fact that the alkyl groups are electron releasing in nature, and they will make sure that the positive charge is going to get basically distributed, and it'll make sure that this particular carbocation is stable. Now, this best and latest technique for isolation, purification, and separation of organic compounds is obviously chromatography. Chromatography is so unique. You can separate it. You can isolate compounds. You can purify them. So you can remove the impurities, and you can also separate them. Not only that, you can also check if a particular compound is pure using the using chromatography. This particular thing is its applications are so, I mean, there are so many applications and it's quite interesting, and it's one of the latest techniques which are used for isolation. I mean, there are updated versions, like you have various stationary phases, mobile phases coming up, but yeah, chromatography is one of the best and the latest techniques. There is the reaction over here we've been given. First of all, we need to classify it. So if you remember, we discussed this in one of the textbook questions. First of all, this is a substitution reaction, right? Because the I is getting removed and OH is getting added. Right, makes sense. I gets removed, OH comes in, so it's a substitution. Now, we've been given these two words, electrophilic and nucleophilic. Electrophilic means an electrophile is going to come and attack, whereas a nucleophilic means a nucleophile is going to come and attack the compound. So in this case, K plus and OH minus, if you think about it, potassium will get a positive charge, OH will get a negative charge. And this OH minus is a nucleophile because it is electron loving. So it's a nucleophile, and oh, sorry, I am so sorry. OH minus is a nucleophile. It's a nucleus loving, so it is electron rich. So it will attack this carbon atom, and I mean, you learn about the reaction in itself in detail at a later point, but OH minus is a nucleophile. So this particular reaction is a nucleophilic substitution reaction. With that, we are done with the textbook exercises for this chapter. I know I have not done the quantitative analysis of organic compounds. I plan to upload the videos in some time, but I realized that at this point, since it's 2021, I realized that you are not learning qualitative and quantitative analysis of organic compounds. So I think even I'm not sure, but I think even the various methods of purification is not included in the syllabus for this year. So for now, I've just uploaded these. In a few days or like after some time, I will be uploading the videos for the quantitative analysis as well. With that, we're done with the chapter, organic chemistry, basic principles. These are all very important, and these will actually help. It'll help you a lot if you learn these properly right now, especially next year where you have to learn about individual functional groups and their reactivities, their reactions, their intermediates. All of that is again to do with the basic things that we learned in this chapter. So if you still have a few doubts about them, feel free to reach out to me. I love to help. That's all.